Hi everybody, this is Mr. Zarzak, and in this video I'm going to take you through an example problem that connects together work and energy and friction and springs. Let's go. Alright, so here we go. We've got a crate. It's got a mass of 55 kilograms. It's suspended, which stretches the spring 0.11 meters. Next, the spring is compressed 0.3 meters as shown. Used to propel the crate to the right. The crate achieves a max velocity of 2 meters per second. What's the coefficient of friction between the crate and the ground? Okay, so I'm going to break this up into 3 different parts. Okay, so I'm going to call this one like part 1, part 2, and part 3. Okay, it's one big question when we get to this coefficient, but we need to use all these things to get to that. Okay, so first one, it says crate below has mass 55 kilograms. It's suspended. Okay, so now, important word there. Okay, suspended means we're going to hang it at rest. So like if you suspend something from some rope or some wire, or in this case, a spring, okay, it's just going to hang there motionless. All right. Why would we do this? Well, if I take and I hang it, it's going to be in equilibrium. Okay, so if I take and I draw a little FBD here, if I draw a little FBD here, okay, for this hanging mass, hanging from a spring, okay, well, it's being pulled down by its weight, so it's got this force of gravity here. Okay, and the spring is pulling it up. Okay, and the key word here is it's suspended. All right, so when I write my net force equation here, so I'll make up my positive direction. All right, so then my spring force minus my weight is equal to ma. Okay, but again, if we're suspending it, well, then there is no acceleration. In which case, we're in equilibrium, which means that the forces add up to 0, or the forces equal out or are balanced, which means that if we know the equation for the spring force, which we do, it's Hooke's law, okay, we can now take and we can calculate the K, the spring constant. So that's what I'm going to do here. So mg over x is equal to K. All right, the mass here is the mass we hang, so, all right, we take this crate and we're going to hang it, all 55 kilograms, and when we do this, this spring here is going to stretch 0.11 meters. All right, so 55 kilograms, okay, and either 9.8 or 10 for gravity. I'm going to use 10 for gravity for this problem simply because the numbers work out a little nicer. Okay, 55 times 10 divided by 0.1 comes out to 5,000. Okay, that's my spring constant, and this would be newtons per meter. Okay, so from number 1, I can get this K value. Okay, and it's not the answer to the problem. I'm looking for the coefficient of friction. Oop, come on, I just want to make this red. Be red. There. Okay, great. So I'm going to use that in number 2. Okay, and again, it's the spring constant, so it belongs to the spring. It's not going to change. All right, so the spring is compressed 0.3 meters as shown, and it's used to propel the crate to the right. Okay, so what we're staring at here is we're going to take, and this spring here, it's already compressed, which means that there's energy stored in it. Okay, we're going to use this here. So PE, what I'm in green now, I got to switch colors. Okay, so this is PE spring. Okay, so we store some energy with the spring, okay, and then we're going to use it to propel the crate to the right. So the crate is going to get shot this way. Okay, this 0.3 meters. All right, so from here to here, let's line them up at the spring, I guess, here. So from the edge of the spring, okay, until the spring uncoils, okay, that's my 0.3 meters, which means that I had to compress the spring 0.3 meters. That's my X, okay, that I'm going to get in when I compress the spring. Now, what it's going to do here is it says it takes it, it makes it achieve a velocity, a max velocity of 2 meters per second. See, so like over here, okay, the thing is going like this way, okay, at 2 meters per second. All right, now if it's moving, well, that means the crate has kinetic energy. Okay, but the hitch is that this says that there's a coefficient of friction between the crate and the ground. See, so if I just try to set up conservation of energy, and I'm going to set up conservation of energy. Here, let's do that over here. So conservation of energy just says that the initial energy has got to be equal to the final energy. Okay, so this spring potential energy that I have when I compress the thing, so it's like a little like initial, okay, is going to become kinetic energy, all right, but it achieves a max velocity. We'll see it when we do the math. That's too slow because there's friction. Okay, if this was frictionless, it would be going faster. But there is friction, so it's not going as fast as it could, okay? And so the way that we balance conservation of energy, or the way that what we have to do to make this work is we have to put in this extra little term for the thermal energy, okay? So things heat up, all right? So if I calculate this, all right, so the P spring, that's half K x squared is equal to 1/2 mv squared plus this thermal energy. Okay, now I'm going to use the value that I got from question number 1 over here, or what I called question 1. The K value is 5,000 newtons per meter. Okay, so that part still holds true, so I'm just pulling that over here. So newtons per meter. Okay, and I take and I compress this thing, I should say, 0.3 meters. All right, when we're using this spring potential energy, don't forget to square that x. All right, so that's equal to 1/2 times the mass. It's still the same 55 kilogram crate. Okay, and it achieves this speed, for this velocity, I should say, of 2 meters per second. So it's moving to the right at 2 meters per second. So 2 meters per second. Okay, and also don't forget to square the velocity. Okay, and we're going to see that just the numbers there don't balance because there's this extra thermal energy. Okay, so we get this heat. All right, so we put this on my calculator, and less than I'm going to get 225. Okay, now this would be joules. All right, so here, I'll just write it just to say that I did. Look. Okay, and then this half 55 times 2 squared is going to be 110 joules. Okay, and the remainder, what should have been, or what could have been, I should say, kinetic energy, never got to it. It was transformed into thermal energy. Things heated up. Okay, so how many joules of this do we have? So subtract over that 110. So what I get 115 joules of thermal energy. Okay. So what? Well, that thermal energy is created by friction doing work to take energy out, to take away mechanical energy. Okay, and well, if we got this much thermal energy generated, this 115 joules, well, that means that's exactly how much work friction did to take out that energy. Okay, so remember, work can be positive or negative. All right, positive work adds energy, negative work takes it away. So what we have here is that this work that gets done by friction is going to be negative 115 joules. Okay, all right, and so again, this is what I got from I'm calling this part number 2. Okay, so I'm just going to mark that as a number 2. Now, we could also solve this not just with energy, but we could look at it from the perspective of work. Okay, so just as a check, okay, I'm over here, just a check. Okay, remember, all right, that work is equal to the change in energy, okay, and this delta E, this change in it's the final minus the initial, see? So like what happens is the spring energy, that's the initial energy, so it starts with this PE spring, okay, and it winds up having some kinetic energy. So like, final minus initial, the change in energy. Okay, and if I do that, well, that kinetic energy, we calculated that. That's what we got from doing this 1/2 55 times 2 squared. Okay, so that's the 110 joules. All right, and the spring energy, that was our initial energy. That was the 225 that we found over here. So minus 225. Okay, so then if we're talking about this work that gets done by friction, okay, well then lo and behold, what do we get? Negative 115 joules, which just means that the friction took 115 joules of energy out of the system, out of the crate, okay, and the spring, all right? So there we go. All right, great. So we've got agreement. We like that. Do you agree? I agree. Great. Let's agree to agree. All right, on we go. All right, now we can get to what we're really after, which is what is the coefficient of friction between the crate and the ground? Okay, so for number 3, we're going to kind of do combo here. All right, in the first part of the problem, we applied forces, and then we did work and energy. Well, now we're going to do a little bit of both. Okay, so as the crate moves, okay, well, it's also displaced as it speeds up to this 2 meters per second. See, so I can also think of this, all right, as how far the crate gets displaced. It gets pushed sideways the same 0.3 meters. See, so if I compress the spring 0.3 meters and let it uncoil, okay, well, it's just going to uncoil right back out, all right, that same 0.3 meters, all right, no more, no less. Okay, now if I think about this from the perspective of forces, okay, so I got another free body diagram, okay, but now this free body diagram is about the crate as it's moving along the ground. See, so like it's displaced this way, this is 0.3 meters, okay, and that's not part of the FBD, all right, but I want to keep it in mind because as I label here, well, here, so I've got the gravitational force or the weight of the thing, okay, it's moving along the floor now. So I also have some normal force acting upwards, okay, and if it's moving to the right, all right, well, that means the friction here is acting to the left, okay, and to be correct and thorough, okay, well, the reason the box moves to the right is because, well, the spring as it uncoils, it's pushing it to the right, okay, so there's 4 forces here, all right, now, I'm going to start by looking vertically, okay, and let's say that up is my positive direction. All right, so stay with me here. So then I've got positive normal force, negative weight. Okay, so net force equals MA. All right, and I'm making a distinction here. This is vertical acceleration because as the spring uncoils, all right, the box doesn't accelerate up or down. It does accelerate sideways, okay, but no up or down, in which case, well, then the normal force is just going to be equal to the weight. Okay, so Fn minus Fg is equal to 0, so move that Fg over. Okay, that Fn is equal to mg. Now, why do I care about that? Well, ultimately, what I'm really after now is what's the coefficient of friction. So I got to get that coefficient of friction in there somehow. So I always remember that friction is the force that makes physics fun. F of F is equal to mu F of N. Okay. All right, so there's the forces bit. All right, now to get to the coefficient, I'm actually going to take, well, actually here, I should write this out first too here. So F of F is equal to mu mg, just sub that in, okay? So anyways, so now that I've got that relationship established for the friction, okay, well now I'm going to go and I'm going to look at this from the perspective of work, okay? So work is just equal to force times displacement, all right? Well, now let's look at the work that's done by friction. I know what the number is, okay? It's this negative 115 joules. I got that, all right? I'm going to deal with that in just a second, okay? Well, this frictional force here, all right, look, the displacement is to the right, the friction is to the left, okay? So I have 2 vectors here that are both involved in my calculation, so I got to pick a positive direction. So I'm going to pick positive to the right, which means that my d value, my displacement would be a positive, what is it, 0.3 meters, but my friction force is going to be negative, okay? And I have to account for those 2 things when I'm computing work. See, work can have direction and energy does not, okay? Now, I could just as easily have flipped this around and say, oh, well, let's make the positive direction to the left. Ha, 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 ha. Now the friction's positive. Yeah, but then the displacement's negative. See, these 2 things are always going to be in opposition, all right? So that's the kind of the concept that's behind there. All right, so then all I really need to do now, okay, is I have a relationship for friction. So minus mu, well, let's write it in purple, minus mu mg, okay, times this distance. Oh, we'll get really fancy because this is the blue problem. Okay, so times the d. All right, and now I have everything I need now to find the coefficient, which is what I'm after. Okay, so I'll put the blue in for the answer, but just to keep it simple, I'm going to take and just write everything in black here. So I get mu mg times d. Okay, the leftover here is the mu. So then now let's sub in here. All right, so that work that gets done by friction, okay, that's the negative 115 from above. All right, take that, divide that by the mass, 55 kilograms. Okay, notice my negatives are going to cancel here. Okay, so 10 meters per second squared for gravity. Okay, times this displacement, which is that 0.3 meters again. Okay, so if I take and I put that all into a calculator, okay, and I have, all right, we're going to find that this coefficient of friction is equal to 0.697, okay, and this is unit list, all right, the units on the bottom, kilogram meter per second squared, that's force, okay, so that'd be like a newtons times 0.3 meters, newton meter, she's a joule, so I have joules over joules, okay, the units all cancel out, the negatives cancel out, okay, technically speaking, this would be a coefficient of kinetic friction because the box is sliding, and that, ladies and gentlemen, is the answer to the problem. Okay, so lots of good concepts in there. We can use forces, we can use energies, we can use combinations of the 2 along with conservation. All right, Mr. Zayek saying thanks for watching. I will see you next time.